Right, hopefully you can all see that. We're just going to do a couple of examples based on the information that we had last time. So the first example, it's a fairly straightforward one. We're considering two plate electrodes filled with air. The electrodes are 2 centimeters apart and the pressure is 760 torr. Determine the breakdown voltage, and in brackets I've put streamer mechanism. Right, so recall that last time there's a criteria for the streamer mechanism. So we're going to use that. So we know that breakdown occurs when e to the alpha minus eta d, d being the gap distance, 2 centimeters, is equal to 10 to the 8. And note that this is where the number density is high enough to influence the electric field, and this is what causes the additional avalanches, and that leads to breakdown. Right, so if we reduce it further, alpha minus eta d is equal to 18. So we need to find this point on the coefficient plots. We can rearrange the equation. Alpha minus eta is equal to 18 divided by 2. Just be careful of the unit there. Your coefficients have the same unit. It's okay then. We need to account for pressure at 760 torr, and that gives us a value of 0.012 per centimeter per torr. Right, if we go to our plot, we can find it on the alpha minus eta plot. Right, I think it's somewhere around there. You can just confirm that yourselves. So I have found that at a field of 39.5 volts per centimeter per torr, that's where streamer breakdown occurs. So the voltage would be equal to 60 kV. Alternatively, you can randomly select values and you can just iterate. So you'd select a small value, a large value, and just iterate until you find your breakdown voltage. Right, the second one is an example of the streamer breakdown between two spheres. I've listed the equations there. I'm just going to jump to my other screen and draw something for you. Right, there's a thumbs up. That's good. All right, so we're looking at two spheres. I'm going to put a voltage here on one of the spheres. I'm going to put 0 volts on the other. I'm going to show that they're separated by a distance of s. Right, those equations, basically they said the electric field is related to the charge and the distance apart and the distance away from it. So remember from the videos that you should have watched that the electric field is dependent on charge. So we've got the positive charge where I've put the voltage V, and the negative charge where I've put the voltage 0. Let's start sketching the electric field. Remember, the electric field from a positive charge moves away from it and towards the negative charge. Right, for this, I'm going to come back to the pole and just see what you think about what's happening in this electric field. Hopefully you can all see the poll. There's a statement. Which statement is false? The electric field is 0 kV per centimeter at the midpoint between the electrodes. The electric field is lowest at the midpoint between the electrodes. The electric field is highest at the surface of the two electrodes. If you could all make a guess at which one it actually is. Again, there's no marks here. It's just to get you to engage. All right, I guess everybody's too shy to answer. So which statement is false? The electric field is 0 kV per centimeter at the midpoint between the electrodes. The electric field is lowest at the midpoint between the electrodes. The electric field is highest at the surface of the two electrodes. So let's just quickly go back to the other screen and we can talk about some of it. Right, so hopefully a lot of you watched the electric field videos from those links. So what you can see here is the electric field is in the yellow line. It starts at the positive electrode with a positive charge and goes towards the negative electrode with the negative charge. At no point does it stop. Right, so at no point is it zero here. That makes sense. So the first statement is false. The electric field is zero at the midpoint. That's false. Let's look at the other two statements. If you look at the electric field lines, where are they most intense or where are they closest together? At the electric surface. And it doesn't matter which one it is. They're both equally as intense. Does it matter whether it's 0 volts or not? No, it doesn't. Electric field comes from the charge. Right, what about the midpoint? What can you see about the electric field lines? They're further apart, aren't they? So the lowest electric field is here. But it does not equal zero. There is a place here where the charge does equal zero, but it's actually in the electrodes itself. Remember, your charge always sits on your outside. And that cancels out in the middle. So it's only in the middle of the sphere. It's not anywhere between the spheres. Right, is everybody happy that that makes sense? If you're all happy, you can change your statements to show that which statement is false or not. Right, let's carry on a bit. So there I've drawn it out already. Again, electric field lines close to the sphere are the highest and E is never naught. If you look at the equations, you would have looked at these equations in physics somewhere, but you can see at any instance it's not naught, but it is dependent on the gap distance, the radius of the sphere, and x, which is your distance along the x-axis. Right, so I would normally give you that equation to work with. Let's look at what this means for streamer breakdown in air in a quasi-uniform field. So S, we're going to set at 50. R is the radius of the sphere. We're going to set at 25 centimeters. And P, we're going to set to 760 tall. So the breakdown between sphere gaps is well established. It's published in an IEEE standard. We are saying for a gap distance of 50 millimeters that the breakdown voltage is going to be 138 kV. So that's not for you to memorize. That's just to show that our calculation can get to that. So the first step in looking at breakdown, so the first thing that we're going to do is we're going to assume that alpha has to be greater than eta in the entire gap. Therefore, at the center, where there's the lowest electric field, alpha is equal to eta. Right. So I'm saying in the middle here is the lowest electric field. So if we choose alpha is equal to eta here and determine the electric field there, everywhere else alpha will be greater than eta. So we can go to our coefficient graph and we can see where alpha equals eta. And that's that point there. I see it as 31.75 volts per centimeter per tall. That gives me an electric field at the center of 24 kV per centimeter. So if I then go and work out the electric field at 2.5 centimeters or 25 millimeters, and rearrange the equation, it'll give me a voltage of 122 kV. Right, so it's important to note that this does not mean breakdown will occur. It just means ionization will occur. The second step, this is to solve the streamer equation. So we're going to look at this integral here. Right, so previously we had a uniform field where alpha minus eta d or x would equal 18. So in this case, for a non-uniform field, because the electric field changes, alpha minus eta changes in each section of that. So we're going to look at where that integral across the gap equals 18. We're going to break the gap into a number of components of dx and calculate alpha minus eta for each of those components. In our case here, we're just going to break it into 4 segments of equal length of delta x. Right, we can then calculate E at each point. Right, so there I've got my 2 spheres. I've got my s divided by 2 in the middle, my s divided by 4 close to the negative, and 3s divided by 4 close to the positive electrode. So we're going to calculate the electric field at each point and then refer to the graph for alpha minus eta. Incidentally, E1 will be the same as E3 in magnitude. The direction will be opposite, but in magnitude it will be the same. So again, if we go back to our diagram, or even look at the equation, what you can see, the electric field will be same on the surface, and it'll be the same if it's the same distance away from the surface. So we can calculate E1, starting with the voltage above, and we can see that the electric field is slightly higher than what we calculated before. We can now take that value and we can go back to our graph. From that graph, we can find our eta minus alpha value. And we can multiply that by your pressure. And we note that the values will be the same at the third point. Right, we know from above that E2 is 24.13 kV per centimeter. So that means alpha minus eta is equal to 0. So if we do our integration, we get a total value of 1.9. That doesn't equal 18, therefore we need to increase the voltage that we used here. So let's try at 1.15 times 121 or 122, which gives us a voltage of 138 kV. We go through the same process where we determine the electric field, we determine the alpha minus eta, and then we sum it up as an integral. And then we can see there that that integral is equal to 16.62. Right, this is very close to the required criteria for stream of breakdown, which was 18. There are ways to make it more accurate. We didn't divide it up very much, so we didn't have very accurate values close to the surface of the electrodes. So if we divided it by 8, we'd probably get a more accurate value. If we divided it by 16, it would again be more accurate, and it may be closer to 18. Right. Right, so those are the two examples for breakdown with the electric field, and you can see that you can calculate the breakdown voltage using the streamer criteria to a certain accuracy. The second question, the quasi uniform field breakdown, that's a typical question that will come up in a test or exam. So I've posted numerous tests and exams. So I'd suggest going through this video, going through the notes again, and just making sure you understand that. What I will do is I'll post the two examples with the annotated notes so that you can go through it and work through